Hello students, in this video we will see how to use shortcut method when we have right hand side f of x as a polynomial in x. Okay, so phi of d operates on y is equal to p of x, where p of x is this polynomial a1 x raised to m plus a2 x raised to m minus 1 and so on. So here we will require some results. The first is this 1 plus a raised to n. So this is a binomial expansion, which is 1 plus n times a plus n into bracket n minus 1 upon 2a into a square plus n into bracket n minus 1 n minus 2 upon 3 factorial a cube and so on, where n can be any real number. Remember, n can be any real number, not only natural number. This n can be any real number. This is true. These are the special cases. 1 upon 1 plus a is 1 minus a plus a square minus a cube and so on. And for 1 upon 1 minus a, we have 1 plus a square plus a cube and so on. Now, here, first we will see how to evaluate 1 upon phi of d operates on x raised to m. Once we evaluate for this, then we can evaluate for a whole polynomial also, because this polynomial is nothing but a linear combination of such terms x raised to m, and 1 upon phi of d is a linear operator because it is it's kind of integration and which is a linear, so we can use it here. So first step here is we have to express this phi of d in this form, either 1 plus or minus psi of d or 1 plus or minus psi of d whole raised to r. So yp is equal to 1 upon phi of d operates on x raised to m is equal to, that is 1 upon 1 plus or minus psi of d raised to r operates on x raised to m. Now by binomial expansion we can express this 1 upon 1 plus or minus psi of d raised to r as some polynomial in d by using a binomial expansion. So we'll get here some polynomial in d which operates on x raised to m, and which you can easily calculate because this d is a differential operator and taking derivative of x raised to m is not difficult task. So in general, for a polynomial yp, which is 1 upon phi of d operates on p of x, is equal to 1 upon 1 plus or minus psi of d raised to r operates on a1 x raised to m plus a2 x raised to m minus 1 and so on is equal to a1 times q of d operates on x raised to m plus a2 times q of d operates on x raised to m minus 1 and so on. So this is how we can evaluate yp. So let us have one example. So here we have to find particular integral of dq plus 3d square plus 2d operates on y is equal to x square. So first step is yp. So here our yp is 1 upon d cube plus 3d square plus 2d operates on x square. Now next step is we have to express this d cube plus 3d square plus 2d as 1 plus some polynomial in d. So we can see here, if we take this 2d common here, we will get d cube upon 2d plus 3d square upon 2d plus 1. This operates on x square, which we can further write as 1 upon 2d operates on, now this we can write as 1 plus, so here this is d square by 2 plus 3 by 2 times d. So this bracket term we can call as psi of d operates on x square. Now we'll use this result. One upon 1 plus a, so it is 1 minus a plus a square minus a cube and so on. So we'll use this result. We get yp is equal to 1 upon 2d as it is. This is nothing but 1 minus d square by 2 plus 3 by 2 d plus d square by 2 plus 3 by 2 d square plus minus d square by 2 plus 3 by 2 d cube and so on. And this whole thing operates on x square. Now we can see here we are having all these derivative terms which we are going to operate on x square. Now we know that third derivative of x square is going to be 0. So we can neglect all the terms of d which are having power greater or equal 3, because at that time we are taking higher order derivatives of x square more than of order 2. In that case, all those derivatives will become 0. So we have to consider only those terms which are having power less equal to. So therefore we get here yp as 1 upon 2d, and now this first term we have to take as it is minus, as in first bracket here its degree is 1, so we have to take both the terms. That means d square by 2 minus 3 by 2 d plus, now see from second bracket we'll consider only those terms which are having degree less equal to. So such terms are, so it is like when you are taking a plus b square, so it is a square plus b square plus 2ab. A square will become d raised to 4 upon 4, which we don't require. B square will be, so 9 by 4 d square. The next term will be 2 times product of these two terms, which will contain d cube, that we also don't require, so no need to take that term, minus, now from third bracket, as we are getting cube here, so minimum power of d will be 3. So that's it, we don't require any term from this third bracket, and so on, because after this we are having higher powers of this bracket. So all the powers of d will be greater equal to or greater equal 3, which we don't require. That's it, we can stop here. So this operates on x square, because for all other terms we'll get 0. Okay, so yp is, so what we got here, 1 upon 2d, it is 1, okay, so minus 1 by 2 d square plus 9 by 4 d square. All right, so 1 minus 1 by 2 d square plus 9 by 4 d square and minus 3 by 2 d operates on x square, minus 3 by 2 d, this whole thing operates on x square, which we can write as, so 1 by minus 1 by 2 plus 9 by 4, which is 7 by 4 d square minus 3 by 2 d operates on x square. This is correct, 7 by 4 minus 1 by 2 plus 9 by 4, so LCM is 4, so minus 2 plus 9, 7, yes, 7 by 4, correct. All right, so this is 1 upon 2d. Now let's operate this. 1 operates on x square plus 7 by 4 d square operates on x square minus 3 by 2 d operates on x square. So this will give us x square as it is plus 7 by 4 times second derivative of x square, that will be 2x and then 2. minus 3 by 2 times the derivative of x square, which is 2x. This 2 and this 2 will get cancelled. This will become 2 here. This is 1 upon 2d operates on x square plus 7 by 2 minus 3x. Now still we have to operate this 1 upon 2d. See, this is same as 1 by 2 times 1 by d operates on x square minus 3x plus 7 by 2. And we know that 1 by d is nothing but integration. So we get yp is equal to 1 by 2 times 1 by d operates on x square minus, so what was that term, x square minus 3x plus 7 by 2 minus 3x plus 7 by 2, that is nothing but, so integration of x square is x cubed by 3 minus 3 times x square by 2 plus 7 by 2 times x. Don't take constant term here because the constant term we will get in yc. So whenever we are integrating while finding particular integral, don't include any constant of integration. So this is x cubed by 6 minus 3 by 4 x square plus 7 by 4 x. So this is what yp is. So this is how we can find yp for a polynomial function. Now let us solve one more example here. Okay, so here we will find particular integral of this d square plus 2d plus 1 operates on y is equal to 2x plus x square. So now we have two terms. Same method we will apply. So yp is equal to 1 upon, so we are already having in this form 1 plus d square plus 2d. This operates on 2x plus x square, which we can write as now 1 minus d square plus 2d plus d square plus 2d square plus d square, sorry, it is minus here, minus d square plus 2d cube, so on. This operates on 2x plus x square. So which is, now we have to consider the terms of powers of d up to 2, because again we are having highest power of x as 2. So here we will get 1 minus d square, so no, this is minus 2d plus, from second bracket will require only one term. Okay, we are not going to take square of d square, that will become e raised to 4, that we don't require. Then square of 2d, that is 4d square, that we can take. Next term will be 4 times a d cube, which we don't require. And from other brackets also we don't require any term, because from this third bracket here minimum power will be 3, minimum power of d will be 3. So that's it. So we have to operate only these terms on x plus x square. So this is 1 plus 3d square minus 2d operates on 2x plus x square. So now we can separately operate these terms. So 1 operates on 2x plus 3d square operates on 2x minus 2d operates on 2x plus 1 operates on x square plus 3d square operates on x square minus 2d operates on x square. So that is equal to, so now this is a simple calculation. It is 2x plus 3 times, so second derivative of 2x, that will be 0. So you can see here, if you apply higher order derivatives on this 2x, okay, we get 0 down. So plus 0. Next is minus 2 times derivative of 2x. Derivative of 2x will be 2, that is minus 4. The next term is x square as it is, plus x square. Next, 3d square operates on x square. So 3 times second derivative of x square. Second derivative of x square will be 2. So 3 times 2, that is 6. Then minus 2d, so second derivative of x square. 2 times first derivative of x square, which is 2 times 2, that is 4x minus 4x. So this is our yp, which is x square minus 2x plus 2. So this is how we can find yp for a polynomial function. I hope you understood this. Try to solve some examples. Thank you.